Hello and welcome to another tutorial in this mini-series on calculus at the higher level. And in this and the next tutorial I'll be talking about the topic of stationary points. This can sometimes be a little dry if you just think about it in terms of mathematics, but in fact in the world of science, where calculus is one of the major mathematical tools, stationary points are probably the most important application of calculus, and we'll see why that is as we go through this tutorial. As I say, there'll be probably 2 tutorials on stationary points, and then after that I'll give a tutorial on what is known as optimization problems, and there you'll start to get a glimpse of why the calculation of stationary points is so useful and so important. So let me just motivate why one would think to calculate stationary points. Let's go back to when we first talked about functions. One helpful way I think of regarding a function is, as a metaphor, some kind of machine. You put in a value x and out comes a value y, which is given by applying the machine f to x. So thinking of the function f operating on the input variable x. Now, the power of calculus, as I described in the first tutorial in this mini-series on calculus, is that whereas the function tells you the outcome of the function acting on x, what the derivative does is actually tell you how a change in the input variable x leads to a change in the output, and we might call that delta f of x. And the fundamental statement of differential calculus is that the change in the output, delta f, is related to the change in the input, delta x, by the derivative. And this is strictly true as delta x goes to 0. So we make an arbitrarily small change in the input, we can see what kind of change we get in the output, and what relates those is the derivative of the function at the value of x about which we're making the change in the input. So let's now go from this kind of machine view to a graphical view, and it's by looking at the graphical view that we'll see more clearly why the stationary points will be a very useful thing to know about, and then we'll come back and interpret it in terms of this. So let me just consider some function. I'm just going to draw some essentially relatively arbitrary function here, something with a bit of features to it. So let's say a function that goes up, comes down and goes back up again. And remember that the one way to think about the derivative is that for a given value of x, the derivative at that value of x is telling you about the tangent to the curve at that value. So let me just select a few values of x here just to give you a sense of that. And again, I'm just really recapping things that we have talked about in previous tutorials in this series. But the key idea is that for a given value of x, the slope of the tangent to the curve at that value is indeed the derivative. And in fact, I'm just going to use a ruler to help me draw these because the angle is very inconvenient. So if I just approximate a tangent to the curve at these values of x that I've chosen here, what you can see is that at that value of x, the slope of these tangents is indeed the derivative. And what you can see here is that the slope of the tangent here is positive, so we would say that the derivative for this curve is y equals f of x, and the derivative at this point here is positive because the slope of the tangent is positive. Similarly over here, the slope of the tangent is positive. We would say that the derivative here again is positive. However, in between here, the slope of the tangent is negative, and so here we would say that f primed is less than 0. So it's very important when you're thinking about calculus, particularly in these sort of graphical representations, to be comfortable trying to translate between different forms of words which all actually have the same mathematical meaning, namely the derivative. So we can think of the derivative as a function of x, of a function of x as just f primed of x. We can also think of it as the gradient or slope of the tangent to the function at that value of x. These green straight lines that I've drawn are the tangents at different values of x. We can also use language such as rate of change. We can say that the rate of change of the function here with x is positive, here it's negative, here it's positive again. And all of these forms of language are essentially equivalent and come from thinking about the derivative as relating the change in x around some particular value of x and the corresponding change in y. So, what I want now to draw your attention to are the two most interesting features on this curve are those values of x where actually the curve doesn't change when you change x, and namely these are the minimum here and the maximum here, which actually just by chance is right essentially on the, maybe it's just slightly after the y-axis. So this curve obviously has a hill and a valley, what we would call a maximum and a minimum. And if we draw a tangent to the curve at those 2 points, we see that the gradient of the tangent is 0. The tangents are absolutely horizontal, flat lines. And so at those 2 points, we would say that actually f primed is 0. And that is our definition of stationary points. So for those values of x for which f primed of x is 0, we have a stationary point. And by far the most common types of stationary points are indeed these ones that are shown on this graph here. We have here a maximum, and here we have a minimum. Now there are 2 other kinds of stationary points which are called positive and negative inflection points, and I will just mention those briefly in the next tutorial. They're important to know about, but they are much less common than these, I would say, more important stationary points of a maximum and a minimum. Notice how in the maximum stationary point, the derivative as we increase x goes from positive through 0 and then to negative. So that's sort of a signature of a maximum, is that as x increases through the stationary point, f primed goes from positive to negative, and that's essentially a signature of a maximum. And alternatively, for a minimum stationary point, as x increases, f primed goes from, and let's have a look, you see as x increases through the minimum, the derivative goes from negative through 0 to positive. And so when we in the next tutorial I'll show you more explicitly, but when we calculate the location of stationary points by using this condition, it will be quite straightforward to determine what kind of stationary point we have if we don't have a nice clear graphical view by just looking at how f primed changes through that value of x. Does it go from positive to negative, or does it go from negative to positive? If it happens to go from positive to positive or negative to negative, then we have these other types of stationary points, inflection points, but I'm not going to stress those right here in this first discussion of stationary points. So let's just take a moment to think again about what this really means, though. Again, we're saying that if we have some function of an input variable which gives you an output variable, the derivative tells you how a change in the input translates to a change in the output. And you see the really fascinating thing about stationary points where the derivative vanishes. So for a stationary point, or I should say at a stationary point, we have that delta f is equal to 0 for a non-zero delta x. In other words, around that stationary point, even though I might make a change in the input, there is no corresponding change in the output. And that actually is a very profound statement about a system. And you might possibly be thinking, well, I don't understand, why is that profound? Let me just give you an example. Let's imagine that your function is telling you something about the, let's say, the health of an ecosystem, and your input variable is something like temperature or pH or the number of invasive species. If, as you change the temperature, let's say the health of the ecosystem changes wildly, you would say that the ecosystem is very unresilient or unrobust. On the other hand, if in changing those input variables to the ecosystem you find that the health of the ecosystem is essentially unchanged, then you would say that the ecosystem is resilient or robust. You might use a biological term like homeostasis. There's some kind of balance in the ecosystem where it's absorbing those changes and not allowing those changes to create a change in the system itself. And so the ecosystem in that case has essentially positioned itself at a stationary point. So by finding stationary points in science, we're essentially identifying positions of the system in question where it's most robust. And the remarkable thing about this is that nature seems to care very deeply about this. So for example, you've heard of the term homeostasis with regard to the human body. So if we change our dietary input quite dramatically, our body is able to cope with that, at least over short time periods, because we have a homeostatic mechanism. You could think about a thermostat in a house where you might have changes in the ambient temperature which are then translated to a zero change in the actual temperature because of the heating system turning on or off to keep everything as robust as possible. In physics, we see these kinds of stationary points in many different situations. For example, we see that the entropy of systems is always maximal if they're isolated. Another example is something called the action principle in physics, where the action of a system is always at an extremum. So nature seems to know all about stationary points, and stationary points seem to be the way that nature operates. And that's why when we apply calculus in science, one of the things we're most often doing is, once we've determined a function that describes the system, that tells us how the output of the system depends on inputs. One of the very first things that we will do is to look for stationary points, because those stationary points will give us great insights into not only the behavior of the system, but also where most likely the system will be found in its natural state. So that's a sort of an introduction to the idea of stationary points. And in the next tutorial, what I'll do is just not talk so much about science, but just look at some very simple mathematical examples where I'll show you in detail how to actually calculate the position of stationary points and determine their nature. Are they maxima, minima, or those more exotic inflection points? So thank you very much for your attention in this tutorial, and I'll see you next time.